Welcome back to the Medical Society, and today we're going to be going over general anesthetics. So before I go into my own explanation of it, does anyone really know what anesthetics as a whole are? Anyone? Any ideas?
So localized, essentially numb an area, but general, pretty much just put you to sleep.
Exactly. So if I were to just define anesthetics, you've got a very basic definition as saying the loss of consciousness. And is there any other motive of anesthetics? If I've got someone who's lost consciousness in a surgery, which is a great idea because you don't really want them to wake up and start annoying you in the middle of a procedure, but there must be some other reasons behind it.
Loss of pain as well.
Okay, agreed. So we can say that as analgesia. Any others?
Basically, like numbs any feeling, like depends if it's
Agreed.
localized, yeah.
So it numbs your feelings, and it also does a lack of immobility. So if you're having a surgery done, you don't suddenly want the patient to start moving their hands around even though they're unconscious, which would be a big problem because, I think everyone can understand why that would be a problem. So there's two types of anesthetics, okay? So we've got the first type, which is a general anesthetic. Second type is we've got a local anesthetic. Now in surgeries, like major surgeries, we use general anesthetics, and a lot of dentists, they use local anesthetics, which is basically a daily procedure that a dentist would do. Okay, so now for this part of the presentation, I'm going to focus mainly on general. We'll come to local anesthetics at the end, okay? So let's just rub all of this off. I hope it rubs off, which it isn't, but yeah. Okay, so in general anesthetics, we've got 4 stages. Does anyone have any idea of these stages, or should I just go through them? Okay, go for it.
I'm going to assume the first step, is it sterilization?
Well, no, we're talking about how the anesthetic will actually affect the person.
I'm not too sure what stage this is, but I know they have to weigh you to measure like your dosage because they do it dependent on your weight.
That's pre-procedure. I'm saying like once we've put the anesthetics into intravenously, for example. So what the stage is, I'll just go through them, okay? So the first stage we have is induction. So this is when the anesthetic is intravenously or from a mask put into the person. The second stage is called excitement. The third stage is called surgical anesthesia. And the final stage, which we don't really want to ever reach, which I'll explain why, is called medullary paralysis. So now these are the 4 stages that we have. So in induction, it's the period when the patient will go from a state of consciousness to unconsciousness, okay? So that's the first stage. You want the patient, if you must have seen a lot of videos with the patient counting down and then they suddenly go. That's the first stage, which is called induction, when we go from a point of consciousness to unconsciousness. The next stage is excitement. Now, it's very important because as I said, you don't really want a patient moving around their hands in the middle of a surgery. It's not exactly ideal. So what this will do is it depresses the inhibitory neurons in the CNS, and essentially you'll have an increase in the involuntary movement, which will eventually subside in the next stage. So we've done induction, we've done excitement, and now we've got surgical anesthesia. Now this is essentially the holy grail that we want to reach, because at this point you've got a lot of things that have met your requirements. You've got the patient with a good respiratory action. They're immobile, and they have had analgesics, which means that they're not suffering from any pain. However, if we didn't have anesthetists, we would be in a big problem. Because this stage is like a limbo. You're there, but you're not there. You keep moving around. If you move to the medullary paralysis stage, we've got a massive problem. Okay? If you move back to excitement, again, you've got a massive problem. You've got a patient on a surgical table flapping their hands around, which isn't, again ideal. Medullary paralysis is when you have a failure of their cardiac, of their respiratory system and their cardiac system. And if this isn't reversed quickly enough, it can lead to the patient dying, which I hope everyone can understand is the last thing you want. So that's one of the most important jobs of an anesthetist, to keep monitoring all the signs and changing the drug concoctions to keep the person in the surgical anesthesia stage. So these are the 4 stages of anesthesia that we come across. Yeah, so we've covered that. Okay, so now before I go into any molecular stuff about how this really works, I want to ask anyone, what do you think, like what parts of the body does anesthesia really affect? Any ideas? Abdul?
No.
Okay, where do you think these nerves would be?
So I said the CNS, for example.
Okay, perfect. Any other ideas? Matthew?
So I believe potentially the motor neurons, specifically because we don't want the muscles moving around.
Exactly. I actually think I forgot to mention one thing. So, yeah, so in the surgical anesthesia stage, because you mentioned that, you've got a loss of reflexes. So, especially like motor reflexes. So, a lot of your reflexes are subsided at that point. Because if you hit someone at a point whilst doing a surgery and then they start kicking involuntarily, it's not ideal again. Okay, so now in terms of what the actual anatomical effects of anesthesia are, so we've got effects on the thalamus, the reticular activating system, which I'll just put as RAS. And what these two, when general anesthetics affect these two, it'll lead to a reversible loss of consciousness. You want it to be reversible, not irreversible. Okay? So, reversible loss of consciousness. Okay? So, that's the first thing that these general anesthetics can do. They affect the thalamus and the reticular activating system, causing a reversible loss of consciousness. The next thing we've got effects on the hippocampus, and we've got effects on the amygdala. These are all in the brain. And you've got an effect to the prefrontal cortex. Now, this is a very interesting phenomenon, actually, which I only found out when I went under general anesthetics, is that when you're in them, you wake up, you really still think you were just awake a moment ago. You don't remember anything. Although you might be asleep for around 8 hours, you've got no clue that you were there. And this is caused by something called amnesia. Okay, so it's these general anesthetics affecting these cause amnesia. And that's why you can't remember anything you were dreaming of, for example, in anesthetics, because like I just closed my eyes and I woke up, but it's been 8 hours. And that's the primary reason. And then the last way we've got is something that Abdullah mentioned. You've got it affecting the spinal cord. Now, these all are in the brain, and these are all, I guess, a mental effect of it. These aren't any like bodily effects. But your spinal cord is very important, as Matthew mentioned, for motor, right? You don't want the person moving about. The spinal cord will cause immobility. Okay? So these are the anatomical effects of general anesthetics. Okay, now after this, we're going to go into the molecular effects of how they actually work. And before that, I'm actually going to put out a disclaimer, to be honest. With general anesthetics, it's a bit weird. We've had a lot of theories, like we've had cell membrane theories, and we've had a lot of these hypotheses disproved over the time. So there's no proper, or I guess extremely correct version of anything that sticks around for a long time. Each one gets a better theory coming around and then replaces it. So what I'll do is more of a brief overview of some of the things, which hopefully we can understand, because I was having some trouble understanding a very long 18-page scientific paper. So I came up with this explanation. Okay, so we've got 3 groups of anesthetics, okay? So we'll talk about them step by step, okay? The first group is eomidate. It consists of eomidate, apofol, and barbiturates. This is the first group of anesthetics. Now, what are the effects of them? These are very potent at providing unconsciousness, and hence, because we learned unconsciousness comes in the induction phase first. So these are very important for stage 1. Stage 1 is caused by these three groups of drugs, which are part of the first group of anesthetics that are used. Okay, so these are intravenous agents. If anyone doesn't know what intravenous means, it means essentially into the blood. We inject them straight, so it's into the intravenous. Okay, and these affect our neurons. So if I am to draw, okay, I'll explain exactly how it will work. If I can flip this over. So these agents will affect something called our GABA A. I think it's GABA A. Yeah, GABA A receptors. So these affect our GABA A receptors. Okay. These 3 affect GABA A receptors. Now you must be wondering, what are GABA A receptors? So essentially, if I've got the phospholipid bilayer, let's just keep those as the phosphates. Just do that. Let's grab this. Yeah, I think we can get the general idea. And then, between this, we've got our GABA receptor, which if I draw will be something like this. Okay, so this is our GABA A receptor, and if I just finish that. Oh, I need blue. So that's our phospholipid bilayer, and in that we've got our GABA A receptor. Now it's made out of several subunits, which I'm not really going to bother mentioning because there's no real use of me mentioning it. Now essentially, the way this will function is, if I draw this in more of a textbook format, we'll have our neuron. Okay. This is our neuron, and this bit will be our synapse, and this is the point that the neurotransmitters will be released from, and underneath we've got this, okay, which will just represent here by this, okay. So does everyone understand till now what this is, this diagram? Okay, perfect. Now we've got our neurotransmitters, okay. A whole load of these. Perfect. And these are our GABA, and essentially what we've got is these are carrying something called chlorate ions, okay? So these chlorate ions in normal functioning will move through this and will be controlled by the GABA A receptor. Now what our general anesthetic will do, these 3 groups, is it'll keep it open, okay? This thing will be kept constantly open by our general anesthetic. So when we had a small amount of flow before, which was constantly controlled, now we've got a massive amount of flow of these Cl- ions. Now this disrupts the electrochemical gradient, and also what it'll cause is it'll be very hard for these chlorate ions to actually depolarize the neuron and hence transmit a strong nerve impulse. Okay, if we can't transmit a strong impulse, a nerve impulse, it causes the loss of consciousness. Okay, so I'll just briefly go over it. Can someone let me know the time actually?
It's 35 past.
35. Okay, that's perfect. We're doing good. So it'll constantly let it go through, and if we're not able to stimulate it, because imagine this, right? If I'm pushing onto something just like that, I can't re-push on it, right? I've just pressed against it. I can't do that. I have to move my hand away, and then. So if I'm constantly pushing, I can't do anything. I can't I can't tap it or anything. So I have to stop and then tap it. Okay, the same way here, if I've got my channel that's constantly open, if I want to make a difference, I'll have to push very hard till there's actual movement. The same way, if it wants to make a difference, it has to produce many more of these neurotransmitters to actually cause a strong signal. Whereas before, we had a very small transmission, okay, which meant that a small amount could cause a big change. But once you've got a lot of these already here, there's not a big change anymore. So therefore, we blocked that. Go for it.
So you talked about how these chlorate ions enter through the cell, right?
Sorry, this is a synapse.
So that's the synapse, and the thing through the GABA receptor
Yeah,
is a cell.
this is another neuron.
Oh, it's
underneath.
another neuron.
Yeah, I should have explained that. Yeah. So I just zoomed everything in. Okay.
Right.
So it's essentially a transmission of an electrical signal across the synapse.
So does that neuron want to get rid of the chlorate ions for depolarization?
Okay, so let's take it quite simply, right? At GCSE, we learned that the neurotransmitter will diffuse across the synapse. It'll go there, it'll attach to a receptor. Once it's attached, we've got a signal. We're here. Perfect, right? It's quite simple. It's quite similar here. Okay, we'll just keep it to that point, right? It passes through, causes an electrical signal, right? If it's just jammed, if we've got constantly the signal is passing through, you're not really getting anything. You need fluctuations for the actual impulse to pass through. And if you've got it constantly like this pressed against, you're not going to have any fluctuation, and therefore you don't have any impulse being generated. So that's how we've got our first type of anesthetics working: the eomidate, propofol, and barbiturates. Okay, these cause a loss of consciousness, and this is our GABA. I want you all to remember this quite well, because we'll come back to this at near about the end. Okay, because now we're going to go to the second type. Can anyone take a guess what the second type will do? First type has caused a loss of consciousness. What else do we not want the patient to be doing? Perfect. We don't want them to be moving around. So now we've done this. Now the next one that we have are ketamine, we've got nitrous oxide, and we've got xenon, and we also have cyclopropane. These are involved in the second stage of general anesthetics, okay? So now, he said it'll cause a loss of mobility, okay? Now, these ones, actually, before I give the answer out, what do we think ketamine does? It's a drug. Why do people use it? Do they use it to just have a loss of mobility and just sit there and do nothing? Anyone? Why would ketamine be used as a recreational drug? Why bother if you're just going to lose mobility? Because I think we can just sit down still for that. Avana?
maybe in a small amount it causes feelings of ecstasy and like excitement, happiness, that kind of thing.
Okay, any other ideas? No? Okay, Matthew?
I don't know if this is true, but is it a depressant that like slows down all of your brain activity?
Perfect. So what we've got here is an analgesic, okay? So what this will cause is it'll cause a suppression of pain, okay? We don't want the patient to be experiencing pain, especially when you're pressing the skin with a sharp scalpel and blood going all around and the patient being in a horrible state. We don't want them to be feeling that, okay? So this will cause, this is called an analgesic and causes a suppression. Analgesic causes a suppression of pain. So reduced or no pain. These three, ketamine, nitrous oxide, xenon, and cyclopropane, analgesic drugs, reduced or no pain. And this is what we need.
It's kind of hard to see the letters. Quite bright.
Okay, okay, right. I'll shift the color. Okay, now you might ask, wait, we've got these three drugs. What was the point of the first one? Surely these can do everything. No, these are very bad at producing unconsciousness, like a complete state of unconsciousness. So they've got separate functions, and this is its only function in this context, okay? Now, this doesn't affect the GABA receptors, okay? It doesn't affect the GABA A receptors. Instead, it affects something called the NMDA receptors. NMD, not B, NMDA receptors. Right, okay. So now these receptors are found on our spinal cord. In the spinal cord. The NMDA receptors found in the spinal cord. Now, how do these actually work? Okay, so because they're not affecting the GABA receptors, they're not doing anything to it. The chloride ions are functioning perfectly. They're having a good transmission there. So that will only be affected by our stage 1. So if it's analgesics, what stage will this be used in? If it reduces pain, what stage? Sorry?
Excitement.
It's the stage after, because surgical is when you're cutting the person. So you want the person to be painless. So this is used in stage 2, okay? This type of anesthetic. Okay, now let's understand how this works. I'm going to draw a diagram out for this. Now we've got another channel protein here. This is quite interesting, especially like when we look in textbooks, channel proteins look a bit useless at times. And it feels a bit more context with this.
Vedant,
Yeah.
we've got 3 more minutes.
Really? Yeah, we're not going to finish this, are we? Anyways. Okay, so we've got intracellular neurotransmitters being made. These neurotransmitters will pass out through here and diffuse across the synapse. Now what will happen here will be unlike from before. Here we'll have something called non-competitive inhibition, okay? Now this is something that we learn in A-level biology, and for the sake of people who don't do A-level biology, I'll just very quickly whiz over it. So essentially, if we've got an enzyme, and let's say this is our enzyme, okay? And maybe this bit is our active site, okay? That's our active site. And we've got something else called our allosteric site here, which will be here. And you'll get a non-competitive inhibitor binding to this bit, right? Or just attaching them. Now this will cause, essentially, just to keep it simple, it'll cause a change to the tertiary structure, or just the structure of the enzyme, and will cause this active site here to change shape. And if it's changed shape, then you've got a problem, okay? And the problem is, you can't attach to anything. However, this is a channel protein, so for this, it'll cause a change to the tertiary structure and will mean that these neurotransmitters cannot effectively bind and pass through here, okay? So that'll cause a problem and we won't have any transmission of any neurotransmitters and therefore a nerve impulse. So now this is how the first two groups of general anesthetics actually work. The third type of general anesthetics, which I'll go over quite quickly because I realize we're running out of time. We'll leave local anesthetics for next time, or sometime later. Okay. So the third type we have are halothane, and enfurane. Now, the great thing about this is I don't have to explain anything now, because it's the same way that the previous two were doing it. It combines both of them and does it. It's got both functionalities. However, the functionalities aren't strong enough. Now, essentially, they'll inhibit immobility. They'll cause the person to be immobile and won't be able to move. And with the combination of these three drugs, these three types of anesthetics, we get the person into our surgical state. And therefore, the person is in a state that they're ready for surgery and they can be carefully monitored by an anaesthetist. I hope you found that mildly entertaining and informative. Thank you.